Hello and welcome to the Snoozy Scientist, where we explore life's deepest secrets, one sleepy yawn at a time. Tonight we're drifting together into one of the most enchanting questions ever asked, a puzzle that has danced through our stories, our science, and our wildest dreams for centuries. Could it really be possible to step outside the flow of time, to visit tomorrow before it comes, or to wander back into yesterday and stand where history was still being made? From ancient myths of time-bending gods to the swirling galaxies of modern science fiction, the idea of time travel has always tugged at our curious minds. But behind the fantasy, there are real clues hidden in the laws of physics, hints from black holes, speeding satellites, and quantum puzzles that suggest time may be more flexible than we ever imagined. Even with all our powerful equations and telescopes reaching out into the deep, starry night, so many questions remain. Could we ever build a real time machine? Why does the universe seem to protect its past? And what secrets might still be waiting in the folds of space and time, just beyond our reach? Before we wander too far, I'd love to know, where in the world are you listening from tonight? Drop a comment and tell me what time it is where you're drifting off. And if these gentle rambles help you float away to dreamland, please tap like and consider subscribing. It keeps this snoozy corner of the internet alive and means so much to have you here. Now fluff your pillow, take a slow deep breath, and let your mind open wide. We begin now. Why are humans obsessed with time travel? Since the first time a human gazed up at the stars, we have wondered not just where we are, but when we are. We mark the seasons by the tilt of the sun, we measure the years by the lines on our faces, and we hold the moments that matter most like delicate glass ornaments tucked safely in the corners of our minds. Yet for all our clocks and calendars, time remains one of the most elusive threads of life, always moving forward, never letting us press rewind. This quiet fascination with time is stitched deep into our stories. Long before anyone scribbled equations about space-time on chalkboards or built satellites that drift high above our heads, people gathered around firelight and whispered tales of stepping into other times. Across cultures and continents, we dreamed of gods who could wander centuries in a heartbeat, or mortal heroes who might leap into the distant past to change the course of history. In ancient Hindu mythology, there are stories like that of King Ryavata, who traveled to the heavens to meet the creator Brahma. When he returned to Earth, he discovered that countless ages had passed, and everyone he had ever known was gone. In Japanese folklore, the tale of Urashima Taro tells of a fisherman who rescues a turtle and is rewarded with a visit to a magical undersea palace. He stays only a few days, but when he returns to his village, centuries have slipped by, and all that once was familiar has crumbled to dust. These old tales remind us that the idea of time slipping away, or us slipping away from time, is older than any telescope or theory. As the centuries turned, our longing to escape the arrow of time only grew stronger. When the first printing presses filled bookshelves with pages and pages of human curiosity, a new wave of thinkers and dreamers began to shape this timeless wish into something more than just a legend. One of the earliest seeds of modern time travel fiction can be found in the stories of Charles Dickens. In A Christmas Carol, Ebenezer Scrooge is whisked away from his cold bed by the spirits of Christmas past, present, and yet to come, forced to face the shadows of what was, what is, and what might be. Even then, we see the early bones of what would become a cultural fascination, a chance to visit our regrets, to right our wrongs, to peek ahead and ask what if. But perhaps no one gave that longing a more iconic push than H.G. Wells. In 1895, Wells published The Time Machine, a slim but powerful tale of a lone inventor who builds a machine that can ride the currents of time like a ship sailing across an ocean. Wells's vision was so vivid, so believable in its scientific flavor, that it planted the idea in millions of minds. Maybe, just maybe, one day we could do this too. The time traveler in Wells's book did not just want to see the future, he wanted to understand the forces that shape humanity, to stand on the shores of time's endless sea and watch empires rise and fall like waves crashing onto sand. It was fiction, but it carried a seed of science. It whispered that with the right gears, levers, and equations, the past and future might someday be within reach. In the decades since Wells's fantastical machine first fired up in the pages of his book, our obsession with time travel has only grown. We built entire worlds on it, vast universes where phone booths and blue police boxes spin through centuries and light years. Fans of Doctor Who know that the TARDIS is far more than a prop. It is a symbol of our belief that time, however stubborn, might one day bend to the will of our curiosity. When the Doctor leaps between distant centuries with a grin and a flick of a switch, it feels like an echo of our collective dream, to break free of the hourglass, to outrun the clock, to see all the stories we were never alive to witness. And who could forget Back to the Future? A story that turned a DeLorean sports car into a vessel that could streak across the calendar with a burst of fire and a trail of dreams left behind. Marty McFly's adventures showed us the thrilling chaos that might come if we could tinker with our own timelines. We laughed at the paradoxes, the awkward dances, the accidental erasures. But beneath the humor was something tender, a reminder that so much of what makes us human is tangled up in the moments we wish we could relive or rewrite. Whether it is the ancient fables of kings lost to centuries, the Victorian dreams of H.G. Wells, the adventures of the Doctor, or the sparks that fly when Marty slams his foot on the gas pedal, the story is always the same at its core. It is our story. We are creatures who remember. We are creatures who hope. And somewhere in the soft spaces between those two, we will always wonder if we might find a way to slip the bonds of the ticking clock, just for a little while. So tonight, as you lie there listening, let your mind drift through those ancient palaces and flickering movie screens. Imagine yourself peeking through the crack in the door of time, feeling the past brush against your fingertips and the future waiting like a warm lamp in the distance. It is this timeless curiosity that keeps us searching, keeps us studying, and keeps us dreaming long after the last page is turned or the credits roll. What is time? If you close your eyes and listen, you can almost hear time passing. Maybe it is the soft tick of a clock on your bedside table, or the whisper of a breeze slipping past your window as another hour drifts by. We feel time every day, in the warmth of the sun rising and setting, in the changing of the seasons, in the quiet lines that slowly appear at the corners of our eyes. To us, time seems so ordinary, so constant. It marches forward, steady and straight, and we ride along with it whether we notice or not. But what is time, really? For thousands of years, people thought of time as an invisible river flowing in one direction, from the past through the present and into the future. We invented ways to measure its flow, carving lines on sundials, building water clocks that dripped out the hours, drop by drop, and eventually crafting tiny gears and springs that kept time ticking even while we slept. The ancient Greeks thought of time in more than one way. They spoke of Chronos, the relentless linear time that devours everything. But they also spoke of Kairos, the fleeting, opportune moments that seem to stand outside of ordinary hours, moments when time feels somehow thicker, more alive. It was not until a little over a century ago that our understanding of time was cracked open and made new again. Before that, physicists like Isaac Newton saw time as an absolute backdrop to the universe, a giant cosmic clock that kept everything in order, whether we were watching or not. It was steady, universal, and unchanging, the same for you as it was for me, the same for the sun as it was for a falling apple. Newton's universe was like a stage, with time and space as the boards beneath our feet, solid and reliable. Then came a quiet thinker with a mind full of wild ideas. In the early 1900s, Albert Einstein proposed something that would turn our picture of time upside down. His theory of special relativity suggested that time is not separate from space at all, but woven together with it in an intricate fabric called space-time. Suddenly, time was no longer the universal metronome we thought it was. Instead, it became something flexible, something that could stretch and squeeze depending on how you moved through the universe. Imagine space-time as a giant blanket spread out beneath the stars. If you drop a heavy ball onto the blanket, it will sag and bend. This is what happens when massive objects like planets, stars, or black holes sit in space. They bend the fabric of space-time around them. And when space-time bends, so does time itself. Clocks tick more slowly the closer they are to massive objects. Time flows differently for an astronaut circling a planet than it does for someone standing on the ground below. This idea feels almost magical, but it is not just a dream scribbled out in equations. We have measured it. We know that astronauts on the International Space Station, moving at incredible speeds high above Earth, age just a tiny bit slower than people on the ground. We know that the clocks and GPS satellites have to be adjusted every single day because time runs differently for them than it does for us. Without these adjustments, your phone's map would quickly become useless. The directions you rely on to find your way home would lead you miles astray, all because time is not as rigid as it seems. When we talk about time as a dimension, it helps to think of it like a path we walk along. You can move left and right, up and down, forward and backward through the 3 dimensions of space. But in time, we appear to only move forward. Why is that? Why do we remember yesterday, but not tomorrow? Some physicists think this is tied to entropy, the tendency for things to go from order to disorder. A glass falls off a table and shatters, but you never see the shards leap back together. This one-way street, called the arrow of time, seems to keep us moving ahead. Yet even this arrow might be an illusion, a trick our minds play on us as we try to make sense of our lives. In physics, especially when you look at the deepest laws that govern particles and forces, many equations work perfectly well, whether time is moving forward or backward. Some scientists believe that the past, present, and future all exist together in what is called the block universe. Imagine the story of your life not as a movie reel unspooling in front of you, but as the whole film, every frame existing at once. You stand in the present frame, but the past and future are just as real. You just cannot visit them, at least not yet. So when you hear that time is a dimension, know that it is not just poetic language. It means that time has structure, that it is connected to the stars that spin above you, the ground that holds you, and the light that streams across the endless dark. It bends when you move fast. It twists when you stand near a black hole. And in the gentle hush of the universe, it is always there, wrapping us in its soft, invisible fabric. As you lie there tonight, letting your thoughts drift, imagine time not as a ticking clock, but as an ocean. Each wave is a moment, passing you by, touching you briefly before rolling away. Some waves carry memories of the past, others promise dreams of the future, and somewhere far out beyond the horizon, they all come together, past, present, and future, waiting for curious minds to find a way to sail them all. If you close your eyes tonight and let your mind drift into the hush of the universe, you might picture a giant, silent clock ticking somewhere among the stars, each swing of its pendulum marking every moment that has ever been or ever will be. For centuries, people believed that time was just like that, a cosmic metronome, steady and unwavering, ticking out its perfect beat no matter where you stood or how you moved. Time, they thought, was absolute. It was the same for you as it was for a king, the same on a mountaintop as in a valley, the same today as it was in ancient days. That picture of time, constant, universal, unbending, guided some of the greatest scientific minds for hundreds of years. Isaac Newton imagined the universe like a grand, predictable clockwork. He saw time as a backdrop, an invisible stage on which all the stars, planets, and people moved. Everything in nature danced to its steady rhythm. If you set two clocks side by side in Newton's world, they would tick in perfect harmony forever, no matter how far apart you moved them. But in the early 20th century, a quiet, thoughtful man with wild hair and a twinkle in his eye dared to ask, what if time was not quite so rigid? What if it could bend and stretch the way space does? That man was Albert Einstein, and his ideas would change the way we see time forever. In 1905, Einstein published his theory of special relativity. It was a small paper, just a few pages long, but inside it lay one of the most mind-bending ideas in the history of science. He proposed that time and space were not two separate things, but two parts of the same fabric, a fabric we now call space-time. Instead of imagining the universe as objects moving through an empty stage, Einstein showed us that the stage and the actors are connected in ways no one had fully realized before. Picture a blanket stretched tight. If you drop a heavy ball onto it, the blanket sags and curves around the weight. Einstein's insight was that massive objects like stars and planets do the same thing to the fabric of space-time. They create dips and bends that affect how everything around them moves, including light itself. Suddenly, space was no longer just empty distance. It had shape and texture, and so did time. But Einstein did not stop there. He showed that the way you move through this fabric can actually change how time passes for you. The faster you move, the more time slows down. This is not just an idea in a book, it is real, proven physics. Imagine two twins. One stays on Earth while the other climbs into a spaceship and flies near the speed of light. When the traveling twin comes back, they will have aged less than their sibling. They will have skipped ahead in time. This is known as time dilation, and it is not just a thought experiment. We see it happening all the time in the world around us. Astronauts who spend months orbiting the Earth in the International Space Station return ever so slightly younger than they would have been if they had stayed on the ground. Their hearts beat in a world that moves a little faster than ours. Even the satellites that help your phone's GPS work have to adjust for this effect. The clocks in those satellites tick differently than clocks on Earth because they are moving fast and orbiting high above our planet, where gravity is weaker. Without Einstein's corrections, your GPS would send you miles off course every single day. In his later work, Einstein expanded his ideas into the theory of general relativity, which showed that not just speed, but gravity itself can bend time. The stronger the gravitational pull, the slower time moves. If you stood on the edge of a black hole, where gravity is unimaginably intense, you could watch the entire universe speed by while your own clock barely moved. From your perspective, moments would pass like seconds. For everyone else, entire centuries might unfold. Think about that for a moment. Time is not some rigid ruler that ticks off moments in the same way for everyone, everywhere. It flows differently depending on how you move and where you stand in the universe. This means there is no single universal now. Your now is different from someone's now on a star millions of light years away. The closer we look, the more we see that time is not a river flowing past us, carrying us along. It is a landscape, soft, bendable, changing its contours in the presence of speed and mass. This was Einstein's great gift to us. He showed us that time is not a prison we are stuck inside, but a dimension that can be shaped by motion and gravity. It means that time travel, at least to the future, is not only possible, but already happening in small ways every day. It reminds us that the universe is stranger and more beautiful than any ticking clock could ever reveal. So tonight, as you sink deeper into your pillow and let your thoughts drift outward into that vast star-speckled sky, imagine the fabric of space-time gently curving around you. Picture your heartbeat ticking a little differently than a clock on a satellite far above. Feel the wonder that comes from knowing that time is not a straight line etched in stone, but a pliable living thing, bending, stretching, and whispering its secrets to anyone curious enough to listen. It is easy to think of time travel as something that belongs in the realm of science fiction, a shimmering portal, a flashing time machine, or a magical artifact that whisks you away to ancient days or distant futures. But the truth is, if you take a moment to look closely, you will discover that time travel is not just a fantasy. It is something that happens all around us, every single day, in ways so subtle and precise that most of us hardly notice. You, me, the phone in your pocket. We are all part of this everyday time dance, whether we realize it or not. The secret is something called time dilation. It is a gentle but profound idea that falls right out of Einstein's theory of relativity, and it proves that time is not as stubborn as it once seemed. According to special relativity, the faster you move through space, the slower time passes for you compared to someone who is standing still. This is not a trick or a theory that only works on paper. It is real and measurable, and it shapes our world in quiet but important ways. Picture two people standing at an airport. One is about to board a plane that will soar through the sky at hundreds of miles per hour. The other stays behind, feet planted firmly on the ground. While the passenger sits in that seat, high above the clouds, they are moving faster than the person waiting below. To us, this difference is almost invisible, but to the universe, it matters. The traveler's heartbeat, the ticking of their watch, and even the aging of their cells will happen just a tiny bit more slowly than those of the person who stayed behind. It is not enough to notice with the naked eye, but with sensitive instruments, we can see that time has quietly slipped out of sync. Now imagine taking that idea to an even greater extreme. Instead of a commercial airplane, think about astronauts who live and work aboard the International Space Station. These men and women circle the Earth at an astonishing speed, about 17,000 miles per hour. Up there, they see 16 sunrises and 16 sunsets every single day, and as they drift along this orbital racetrack, they too experience time differently than we do on Earth's surface. When they return home after months in orbit, they are ever so slightly younger than they would have been if they had stayed down here with us. It is only milliseconds, but those fractions of a second are proof that the universe really does bend time for those who travel fast enough. If you want an example that is even closer to your everyday life, you do not have to look to astronauts or rocket ships. All you have to do is open the map on your phone, the GPS that tells you how to get from your cozy bed to the nearest coffee shop or the edge of a national park depends on satellites orbiting high above the Earth. Those satellites move quickly and hover far from the planet's surface, where the pull of gravity is weaker than it is for us on the ground. Both speed and gravity have an effect on time, so the clocks on those satellites do not tick at the same rate as your watch does. Every day, the engineers behind these systems have to adjust for tiny but crucial shifts in time. If they did not, your GPS would grow more inaccurate by the mile. Within hours, it would send you driving in circles or lead you to places that do not exist. The fact that your phone can pinpoint your location within feet is a quiet testament to the fact that time dilation is not just real, it is an everyday part of modern life. Some people like to call this micro time travel. It is not as dramatic as climbing into a glowing machine and punching in a date on a dashboard. You will not step out of a plane or a spacecraft and find dinosaurs waiting on the tarmac, but it is time travel all the same. It is proof that the flow of time is not locked or frozen. It is a river that shifts its current ever so slightly for every traveler who dares to move fast enough or climb high enough away from Earth's gravitational embrace. And if tiny slices of time can slip and slide with a plane or a satellite, what might happen if we could push those limits even further? What if we could build ships that skim the edge of light speed? What if we could hover on the brink of a black hole's event horizon, where time nearly stands still? These everyday examples are small, but they open the door to a universe where the boundaries of time are softer than we ever imagined. Tonight, as you drift closer to sleep, think about all the tiny time travelers above you right now. Satellites circling silently, astronauts drifting through orbit, even the gentle hum of your phone as it catches signals from a clock ticking far away in the sky. Each one is proof that you are living in a world where time is not as simple as it seems. In our ordinary moments, boarding a flight, checking a map, watching a rocket streak across the night, we catch glimpses of a truth that would make our ancestors marvel. Time can bend, it can stretch, it can be shaped by speed and gravity. And in this bending, we find the first hint that real-time travel, however subtle, is already with us every single day. Imagine for a moment that you and your twin stand side by side under a starry night sky. You look up together, tracing the same constellations that have guided sailors and dreamers for centuries. You share the same birthday, the same memories, and the same hope that maybe, just maybe, the universe might hold secrets waiting to be unraveled by minds like yours. But tonight, you and your twin are about to embark on two very different journeys through the fabric of time itself. This is the heart of what physicists call the twin paradox. It is one of the simplest yet most mind-bending ways to understand how time is not as rigid as we once believed. Picture this: one twin stays on Earth, tending a garden, reading books, living a life measured by ordinary clocks that tick away the minutes and hours in their steady, comforting rhythm. The other twin climbs into a sleek spaceship, a vessel designed to travel close to the speed of light, and sets off into the deep black ocean of space. At first glance, you might think their journeys should be equal in the eyes of time. After all, they both carry the same cells, the same DNA, the same heartbeat inside their chests. But the universe does not see it that way. According to Einstein's special theory of relativity, the faster you move through space, the more time slows down for you compared to someone standing still. So as one twin rockets away at near light speed, they experience a strange gift, or perhaps a strange curse, the slowing of time. This is not some invisible magic trick. It is written into the very equations that describe how the universe works. Clocks on the spaceship run slower than clocks on Earth. The traveling twins' watch ticks more slowly. The beat of their heart slows in the eyes of the universe. Even their hair grows more slowly compared to the twin left at home. But for the twin in the spaceship, nothing feels unusual. Time for them moves normally. They eat meals at regular intervals. They sleep and dream and wake just as they always have. It is only when they turn around and come home that the true wonder of this paradox is revealed. After what feels like just a few years aboard the ship, the traveling twin descends back through the atmosphere, the engines roaring like thunder as the spacecraft touches down on the same Earth they once called home. They step out expecting to see their sibling waiting with familiar eyes, but instead they find something shocking. The twin who stayed behind has aged much more than they have. Wrinkles now map the corners of the earthbound twin's eyes. The garden is overgrown, the books have gathered dust, and decades have passed. The twin who left has skipped over the years like a stone skimming the surface of a pond, touching only moments while the water below flows on without them. How is this possible? The twin paradox feels like a contradiction at first, but it is not. It is the natural outcome of how motion warps the passage of time. In this cosmic thought experiment, the two twins did not live the same journey. One moved through space at tremendous speed, while the other stayed rooted on the ground. They followed different paths through space-time, and because of that, time itself treated them differently. The reason for this lies in something called the time dilation effect. When an object moves close to the speed of light, its path through space stretches out, while its path through time shrinks. This means that for the traveling twin, the clock on the spaceship ticks slower than it does for the twin on Earth. The faster you move, the less you age compared to someone standing still. But there is another wrinkle that makes this paradox so fascinating. Some people ask, if motion is relative, shouldn't each twin see the other as moving? Why does the paradox not work both ways? The answer is hidden in what physicists call acceleration and deceleration. The traveling twin does not just drift through space in a straight line forever. They must speed up, slow down, turn around, and return home. These changes break the symmetry and anchor the paradox to reality. The twin who stayed behind on Earth experiences a constant motion, with no sudden bursts of speed or sharp turns. The twin in the spaceship feels the push of the engines, the hum of the ship's frame, the shift as the stars blur and bend around them. This small difference in their journeys is what keeps the paradox from being an impossible riddle. It is what lets scientists test and prove that this is not just a story, it is real. And while we do not yet have ships that can whisk us to other stars at near light speed, the same principles are confirmed every day in our experiments. We see particles and accelerators live longer when they move fast. We measure astronauts aging fractions of a second less than people on Earth. The universe itself reminds us that time does not care about our clocks. It follows its own beautiful, bendable rules. So tonight, as you drift off to sleep, imagine you and your twin standing together once more. One of you older, one of you younger. Imagine the starlight above you, light that has traveled for thousands, sometimes millions of years to reach your eyes. That light is its own kind of time traveler, a reminder that the past, present, and future are all woven together in ways we are only beginning to understand. And maybe, just maybe, the next time you look at the night sky, you will feel a little closer to the cosmic dance that lets us skip through moments, even if just by a few precious heartbeats. If you have ever stood beside a quiet country road and watched a car race past, you know that speed has a way of making the world feel different. The shape of the car blurs. The sound of its engine stretches out behind it like a ribbon in the wind. The faster it goes, the more it seems to slip away from the ordinary rhythm of things. In a sense, that is what happens to time itself when you move through the universe at incredible speeds. The simple truth, tucked away inside Einstein's theory of relativity, is this: the faster you travel through space, the slower you move through time. This idea feels almost magical at first glance, but it is not just an abstract piece of math scribbled in a dusty physics book. It is a real, measurable effect that shows us how deeply motion and time are woven together. And it all comes down to the beautiful balance that exists between how you move through space and how you move through time. If you move more through one, you move less through the other. To see why, let us start by imagining a beam of light. Light always travels at the same speed, about 186,000 miles per second, no matter who is watching. If you are standing still and you shine a flashlight, its beam leaves your hand at that incredible speed. But if you were to chase after that beam in a rocket ship, going half the speed of light, the beam would still race away from you at the same speed. This strange but consistent truth is one of the cornerstones of special relativity, and it is the reason that time must bend to keep the universe in balance. In Einstein's view, you can think of every journey as moving through both space and time together, like two sides of the same coin. When you stand still on Earth, you are moving through time at full speed, 1 second per second. But when you start moving faster through space, you borrow a little from your motion through time. This is not something you can feel. Your heartbeat does not slow down from your own point of view. But to someone standing still, your entire life is gently stretching out. Now imagine a spaceship that could reach an astonishing speed, 99% the speed of light. For the people inside that ship, days might pass normally. They would eat breakfast, laugh with each other, sleep under the hum of the ship's engines, but back on Earth, years or even centuries could pass before they return. It is as if their ship has become a vessel sailing not just through the ocean of space, but also along the edge of time's current, slipping past years like water flowing around a smooth stone. This is not science fiction. It is one of the most profound ways we know that time travel to the future is possible, not in theory, but in practice. Every time we accelerate particles to near light speed in giant colliders, we see them live longer than they would at rest. Particles called muons, which decay quickly when still, can survive much longer when they are moving fast. Their little clocks, if they had any, would tick slower than ours. This same principle applies to astronauts too, though the effect is so tiny it can only be measured with incredibly precise clocks. Still, the proof is there, whispered to us by the universe each time we dare to move fast enough to feel it. Why does speed have this remarkable power over time? The answer lies in the very structure of space-time. Picture it as a vast, flexible grid that holds all the stars and galaxies and planets. When you move through that grid slowly, you use up your motion mostly by drifting forward in time. But when you push yourself to move faster through space, you trade some of that forward motion in time for forward motion through space. The closer you get to the speed of light, the more you spend on distance and the less you spend on time. At the speed of light itself, if you could somehow ride on a beam of light, time would stand perfectly still for you. The entire universe would appear frozen in a single eternal moment. For us, who live in this everyday world of quiet sidewalks and drifting clouds, this truth reminds us of something beautiful: that time is not a cold ruler ticking off moments in an unchanging rhythm. It is soft and alive, sensitive to how we move through the vastness of the cosmos. The faster we go, the more time bends around us, cradling us in its gentle, elastic flow. So as you lie in your bed tonight, drifting closer to sleep, imagine what it would feel like to ride that starship, skimming the edge of light speed. Picture decades passing in the blink of your eye, old friends waiting on distant planets as you arrive almost unchanged. This is not just a dream. It is a promise whispered by the laws of nature themselves that time can be stretched and slowed and shaped by our motion. In every particle that races through an accelerator and every astronaut circling high above the Earth, the proof is there. Time travel to the future is not only possible, it is already happening, one heartbeat at a time. Is traveling backwards possible? Enough to the day became a Tomahoist to the day ball there. Pipe posy to the same recalled, with the very end of claims their snakes. That was the dough, bookies calls the cheat shoeing for the date. Will unused sewer of became, that every tum, and halting there in the plane, for supply for the fit every slicks the Uravan diver to the came, the Euros. If you ask most people what they wish they could do with a time machine, they rarely dream first of leaping into the distant future. The real dream, the one that tugs at our hearts late at night, is the idea of stepping back to see how things really were, back to fix a single moment we wish had gone differently, back to stand at the crossroads where history turned and whisper, maybe just once, what if? In many ways, time travel to the past feels more human than any other idea we have about bending time. It is woven into our stories, our regrets, our hopes for second chances. We wonder what it would feel like to see ancient cities in all their glory, to hear our ancestors speak words that have long since faded into the earth. We imagine being able to reach out through the years and touch the shoulder of someone we loved and lost, to say the things we never had the chance to say. But while time travel to the future is something the universe allows and even encourages in small ways, traveling backwards is a trickier puzzle, one that seems to clash with nature's deep love for order and cause and effect. Physicists have a word for this: causality. It is the simple idea that causes come before effects. You light a match, and then the flame flickers to life. You speak a word, and then you hear its echo bounce from the walls. We live in a universe that seems to cherish this one-way flow of events. It is what gives our stories shape and our memories meaning. Without it, the chain that links one moment to the next would unravel. So, what happens when you imagine stepping back through that chain? At first glance, nothing in the fundamental equations of physics says you cannot. Many of the laws that describe the dance of particles and forces work just as well forwards as they do backwards. If you could watch a single atom's collision in reverse, the math would look exactly the same. But when you gather billions of atoms together into a person, a city, or a planet, you find that the world naturally drifts towards disorder. A broken cup does not leap back onto the table and fuse itself together. Smoke does not drift back into the match. This drift toward disorder is called entropy, and it is what gives us the arrow of time that points stubbornly forward. Yet the dream of traveling backwards will not go away so easily. Some solutions in Einstein's equations hint that closed loops in space-time, called closed time-like curves, might be possible under extreme circumstances. They are strange little windows where, at least in theory, an object could circle back to its own past. But building such a loop would likely require matter with negative energy, something no one has ever seen or held in their hands. Wormholes, theoretical tunnels through space-time, might allow backward travel if one end could be kept in a different time than the other. But to keep the wormhole stable would demand enormous amounts of exotic matter that defies our everyday experience. And then there are the paradoxes. The most famous is the grandfather paradox. Imagine you build a time machine, step back into the past, and accidentally prevent your own grandparents from meeting. If they never meet, you are never born, which means you could not have gone back to stop them in the first place. It is a loop that ties itself into knots, a riddle that the universe seems determined to avoid. This is why many scientists believe there are hidden rules in the fabric of space-time that protect causality. Stephen Hawking even gave this idea a name, the chronology protection conjecture. It suggests that the universe may defend itself from paradoxes by making time machines impossible. Still, others wonder if backward time travel might not erase the past, but simply create a new branch of reality instead. This is where the many worlds interpretation of quantum mechanics comes in. In this idea, each choice, each twist backward through time, might split the universe into another version where both paths exist side by side. You would not change your own past, you would simply create a new one, but that raises its own deep mysteries. Where do all these branches live? And if they do exist, could we ever hope to find our way back to the branch we left behind? In the end, the universe gives us a gentle answer to this longing. Forward is easy, backward is possible, only in dreams and math, at least for now. But maybe that is not so terrible. The past holds us together. It gives our stories a beginning, a middle, and an end. It reminds us to treasure what is here now, because once a moment is gone, it becomes part of the great tapestry that made us who we are. So tonight, as you drift toward sleep, imagine all the yesterdays that live inside you. You do not need a machine to visit them. They are there in the way you smile, the way you remember, the way your heart sometimes longs for a voice you still hear when the world is quiet. Nature might guard its past fiercely, but in your mind, in your dreams, you are already a traveler, wandering through the memories that time can never quite take away. If you have ever daydreamed about time travel, you have probably imagined it as stepping through a portal, a shimmering doorway tucked away in the quiet corner of the universe, just waiting for someone curious enough to walk through. In a sense, that dream is not so different from what some physicists have spent decades wondering about. They even have a name for these cosmic shortcuts, wormholes, or as they are more formally known, Einstein-Rosen bridges. The idea of a wormhole begins with the same mind that reshaped our understanding of time itself, Albert Einstein. Along with physicist Nathan Rosen, he suggested in the 1930s that if space-time is a flexible fabric, then maybe it is possible for it to fold in such a way that two distant points could be connected by a hidden tunnel. Picture space-time as a sheet of paper. If you draw two dots on opposite sides, you could travel across the surface to get from one to the other. But what if you folded the paper so the dots touched? Suddenly, the journey would take only a single step. That shortcut is what a wormhole could be. In the realm of equations, these bridges are allowed by the same mathematics that explains black holes and time dilation. But while black holes are like cosmic pits that trap everything that comes too close, wormholes are imagined as gentle tunnels that offer a way through. One side could open near your home galaxy, the other side could spill you out near a distant star a billion light years away. In that sense, wormholes might be the universe's ultimate secret passageways, hiding routes that could cut across the vast distances of space in the blink of an eye. But if wormholes really do exist, and that is still a huge if, they could offer more than just a clever shortcut through space. They could, at least in theory, offer a path through time itself. Some physicists have suggested that if you could somehow move one end of a wormhole very quickly, close to the speed of light, time would slow down at that end due to time dilation. The other end left behind would stay synced with the normal flow of time. Now imagine stepping through. You could, in principle, enter the fast-moving mouth of the wormhole and emerge from the other end at an earlier point in your timeline. It is a mind-bending possibility, a cosmic door that opens not just across the stars, but backward through the moments you thought were sealed behind you. Yet before you get too excited about hopping through time tunnels to visit the dinosaurs or ancient cities, it helps to remember just how many barriers stand in the way. The biggest problem is that wormholes, if they exist at all, are not exactly friendly places for travelers. The equations suggest they would be wildly unstable. The moment you tried to send even a single particle through, the tunnel would likely collapse in an instant, pinching itself shut faster than the blink of an eye. It is like trying to crawl through a tunnel made of soap bubbles. Touch it the wrong way, and it pops. To keep a wormhole open long enough for you or a spaceship to pass through safely, you would need something called exotic matter. This is not the everyday matter that makes up you, me, and the stars. Exotic matter would have to have negative energy density, a strange property that could counteract the natural tendency of the tunnel to close up. It would hold the wormhole open like invisible scaffolding bracing the walls of a fragile cave. So far, scientists have no confirmed evidence that enough exotic matter exists in the universe to make this possible, and even if it did, the engineering required to shape it and use it safely is beyond anything we can build today. There is also the question of paradoxes. If wormholes could really be turned into time machines, they might invite the same tangled riddles that backward time travel always brings. Could someone travel back through a wormhole and accidentally prevent their own creation? How would the universe guard itself against contradictions that threaten the very fabric of cause and effect? Many physicists believe there are built-in protections, subtle rules that would make a stable, traversable, backward-traveling wormhole impossible. Still, the beauty of science is that it allows us to dream responsibly. Wormholes live at the edges of our equations, a reminder that the universe may hold shortcuts and secrets far beyond what we can see. Some researchers even hunt for indirect signs of them out in deep space, scanning the swirl of galaxies for strange gravitational effects that might betray a hidden tunnel, twisting space-time in its invisible grip. So tonight, as you rest your head on your pillow, imagine for a moment that you could stand at the mouth of a wormhole, feel the air shift as you peer into a tunnel that connects here to somewhere impossibly far away, or maybe impossibly long ago. It is a portal we have not yet opened, a whisper from the mathematics that dares us to wonder if the universe has built-in back doors waiting for someone bold enough to find the key. Until then, they drift in the realm between science and dream, a cosmic promise that time and space might one day reveal paths we cannot yet imagine, and that the greatest journeys may still be waiting on the other side of a fold in the fabric of everything. Among all the strange and wondrous things that dwell in the vast dark stretches of our universe, black holes might be the most mysterious of all. They are places where the rules of nature bend until they almost break, where gravity pulls so powerfully that not even light itself can escape. To some, black holes seem like cosmic monsters lurking silently among the stars. To others, they are nature's ultimate laboratories, showing us how the universe plays with the fabric of reality, including the fabric of time. Long before anyone ever proved black holes were real, physicists imagined them as peculiar solutions to Einstein's equations. According to his theory of general relativity, if you pack enough mass into a small enough space, it will create a bottomless well in space-time, a region so warped that all paths lead inward. This is the black hole's event horizon, the point of no return. Once something crosses that line, whether it is a particle of light or a drifting astronaut, it is lost to the rest of the universe forever. But for all their fearsome reputation, black holes do something extraordinary to time. Their immense gravity slows it down in a way that almost feels like science fiction brought to life. The closer you get to a black hole, the slower your clock ticks compared to someone far away. This is not just a clever idea, it is a truth written into the geometry of space-time itself. If you could hover safely near the edge of a black hole's event horizon, you would find yourself in a kind of time cocoon. To you, moments might pass as they always do, the gentle thrum of your heartbeat, the rise and fall of your breath. But if you could somehow look outward, back at the rest of the universe, you would see something astonishing. While you float in your slow stream of moments, the universe beyond races ahead at breakneck speed. Imagine for a moment that you and a friend are both part of this mind-bending experiment. You stay far away from the black hole, safely orbiting at a distance where the stars still look normal and your clock ticks as usual. Your friend drifts ever closer to the event horizon, protected somehow from the crushing tidal forces that would otherwise rip them apart. From your vantage point, you see their spaceship moving slower and slower as it approaches the edge. Their movements stretch out, becoming more and more sluggish until, just before crossing that invisible boundary, they seem frozen in place. But to your friend, time feels normal. Inside the ship, coffee still steams gently in the mug. Their watch still counts the seconds. They could spend minutes or hours near that boundary, but when they finally fire their engines and escape back to your position, they will find that you have aged by decades, perhaps even centuries, while for them, only a brief moment has passed. This is not just a story pulled from a dream. It is real physics, confirmed by the same equations that guide our satellites and GPS systems. The deeper you slip into a gravitational well, the slower time flows for you compared to the rest of the universe. On Earth, we see this on a tiny scale. Clocks at sea level tick slightly slower than clocks on top of mountains, because they are deeper in Earth's gravitational field. But a black hole takes this to an extreme, turning a gentle difference into a vast ocean of stretched time. Some scientists believe this strange property of black holes could make them the universe's ultimate time machines, one-way machines that carry you forward into the distant future. Hover near the edge for what feels like a week, then return home to find centuries have passed. Of course, the practical problems are enormous. The tidal forces near most black holes would shred any spaceship long before it could park itself at the horizon. But certain massive black holes, millions or billions of times heavier than our Sun, have gentler slopes at their edges. In theory, you could orbit there without being torn apart, if you could build a ship strong enough to resist the radiation and cosmic forces that swirl around these dark giants. Black holes also carry another puzzle. Deep inside, past the event horizon, all our known laws of physics begin to break down. Some believe a black hole's heart hides a singularity, a point of infinite density where space and time are crushed into something we cannot yet describe. What happens there? Does time stop altogether? Or does it continue in some way our minds are not yet equipped to imagine? No one knows for certain. The secrets of a black hole's center remain out of reach, waiting for future generations of dreamers to unlock. So tonight, as you drift closer to sleep, imagine yourself peering at the edge of one of these cosmic wonders. Picture the stars swirling far above, light bending around you like a shimmering halo. Feel the minutes stretch like warm taffy, each second inside your pocket of slow time, while the universe outside spins onward, whole civilizations rising and falling in the time it takes you to breathe. This is the gentle magic of a black hole, a reminder that time is not a ruler, but a river that can pool, twist, and flow at a pace the human heart can barely fathom. And somewhere in that river, among the stars, the secrets of time are still waiting to be found. Every now and then, tucked between the well-tested laws of physics and the experiments we can build in our labs, their lives a strange collection of ideas that feel like they belong in the pages of a science fiction novel. These are the exotic theories, bold, improbable, and so far beyond our reach that they read more like cosmic daydreams than blueprints for machines. Yet they remind us that the universe is full of possibilities, even if those possibilities live only in the elegant folds of mathematics for now. One of the most curious ideas is the Tipler cylinder. This theoretical machine is named after physicist Frank J. Tipler, who in the 1970s took Einstein's equations and asked what would happen if you pushed them to their limits. Tipler imagined an object unlike anything we have ever seen, a cylinder longer than any starship, so massive that its very presence would warp the fabric of space-time. But it is not just size that makes this cylinder so special. It would have to spin, and not just gently like a planet or a merry-go-round. It would need to whirl close to the speed of light, its surface moving so fast that the normal rules of time would start to buckle around it. In Tipler's calculations, if you flew a spaceship along a carefully plotted spiral path around this super-fast cylinder, you could be pulled into a loop in space-time, a closed time-like curve. That loop might allow you to circle back and arrive at the same point you started, but in the past, in this strange dance, you could step out of your ship and find yourself surrounded by yesterday's light, yesterday's footsteps, yesterday's version of you standing there wondering where you went. It sounds like the stuff of dreams, a cosmic tunnel that lets you loop back and witness moments that have already happened. But there are a few problems with this idea that keep it safely in the realm of theory. First, Tipler's cylinder would have to be infinitely long. In our universe, nothing infinite really exists, and any real object we could build would always have edges, which would spoil the effect. Second, even if you could somehow craft a cylinder large enough to come close, spinning it up to near light speed would take more energy than anything we can even imagine producing. And then there is the question of stability. The tiniest bump or irregularity in the spinning giant might collapse the time loops altogether, or create strange, unpredictable ripples that would tear your time machine apart before you ever took your first step into the past. Yet for all its impracticality, the Tipler cylinder stays alive in our collective imagination. It is a reminder that the equations of general relativity are not rigid prison walls, but open doors, hinting at places where time and space might bend into shapes we can barely describe. It is the same curiosity that drives us to look for other, equally exotic phenomena like cosmic strings. Cosmic strings are another peculiar prediction that comes from our best understanding of the early universe. In the first moments after the Big Bang, as the universe expanded and cooled, it may have gone through dramatic phase transitions, like water freezing into ice. Some physicists believe that during these moments, tiny cracks or defects could have formed in the fabric of space-time itself. Long, thin, unimaginably dense filaments that stretch across galaxies. These are cosmic strings, slender threads with mass so concentrated that even a single mile of one would outweigh entire planets. What makes cosmic strings fascinating for time travel dreamers is the way they bend space-time around them. If two strings were to pass close to each other, or if a single string moved at near light speed, the warping effect could be so intense that it might create a loop in time, another closed time-like curve. In theory, you could hitch a ride on this warp and find yourself stepping out at an earlier moment than when you began. It is a beautiful idea, one that ties together the birth of the universe with the possibility of traveling through its history. But just like the Tipler cylinder, cosmic strings live mostly in our equations, not in our telescopes. Despite decades of searching, no one has yet found any concrete evidence that these filaments exist. If they are out there, They may be so rare or so well hidden among the stars that we may never see one up close. And even if we did, harnessing the power of something so massive and so destructive would be a challenge far beyond our current technology. So why do we still talk about these impossible things, spinning cylinders longer than worlds, invisible strings left over from creation itself? Perhaps it is because they remind us that the universe is not just a cold collection of facts. It is a place where imagination and math hold hands and dare us to dream bigger than our tools allow. Tipler cylinders and cosmic strings may never carry us backward through time, but they pull us forward into new ways of thinking, new questions to ask, and new places where wonder lives. Tonight, as you drift closer to sleep, imagine these strange objects out there in the quiet dark. Picture a cylinder spinning faster than light, a thread of space-time stretching from here to the edge of forever. They may be just whispers in the equations for now, but they are also proof that the universe still has secrets waiting for curious minds to find them, and that sometimes the wildest ideas are what keep our dreams moving forward, one sleepy question at a time. There are certain phrases in physics that sound almost like poetry whispered through the halls of the universe. One of these is the idea of a closed time-like curve. It might sound technical at first, something buried deep in the pages of equations and strange symbols, but at its heart, a closed time-like curve is really a simple but mind-bending idea, a path through space-time that loops back on itself, carrying anything moving along it, even you, to the very place and moment where it began. This concept drifts straight out of the fabric of general relativity, the great web of understanding that Albert Einstein spun when he realized that space and time are not two separate things, but one flexible, living fabric called space-time. This fabric can bend under the weight of planets and stars. It can ripple when massive objects collide, and in the deepest corners of Einstein's equations, it can fold back on itself like a ribbon tied into a loop. Imagine walking through a forest trail that eventually circles you right back to your starting point. Now, stretch that idea into the fourth dimension, time. If you could find a closed time-like curve in the real world, it would mean you could start at one moment, travel forward, and come back around to that same moment again, touching the past as easily as the present. In theory, these loops could make backward time travel possible without any spinning cylinders or exotic strings, just the raw curvature of space-time doing what the math says it can do. One of the most famous examples of a closed time-like curve was first proposed by the mathematician Kurt Gödel in 1949. Gödel imagined a universe that was not only expanding, but also rotating. In his rotating cosmos, the very fabric of space-time would twist like a whirlpool. If you sailed far enough in the right direction, you would find yourself moving through a loop that brings you back to your own past. Gödel's solution worked perfectly in the equations, a neat little pocket where the laws of physics allowed time to spin around on itself. But there is always a catch. Gödel's rotating universe does not seem to match the one we live in. Our universe is expanding, but it shows no signs of the kind of global rotation that Gödel described. Other solutions pop up now and then, too, swirling masses of energy or clever arrangements of massive objects that might bend space-time into a loop, but each one comes with its own problems. They may require infinite energy, perfect conditions, or kinds of matter that may not exist at all. Some physicists point to black holes and wormholes as natural candidates for closed time-like curves. Deep inside a rotating black hole, the math suggests there could be a region where space-time loops back on itself. But to reach this region safely, you would have to survive the intense tidal forces, radiation, and the singularity at the heart of the black hole, challenges that seem impossible to overcome. And yet, for all their impracticality, closed time-like curves remain a fascinating puzzle because they show that the laws of general relativity do not automatically slam the door on backward time travel. Instead, they keep it slightly ajar, teasing us with the possibility that the universe may be stranger than we think. If nature allows these loops, even in the smallest corners of reality, they might hold clues about how time works at the deepest levels. This brings us to the big question. If closed time-like curves are possible, why do we not see people from the future showing up on our doorsteps, telling us tales of centuries yet to come? Stephen Hawking famously posed this question in his chronology protection conjecture. He suggested that something, perhaps a yet undiscovered law of quantum gravity, might prevent these loops from forming in the real world. Maybe the universe simply does not want paradoxes. Maybe it has built-in rules that guard its timeline, stitching the fabric of reality closed whenever it threatens to fold in ways that would break causality. But even if closed time-like curves remain out of reach for now, they continue to inspire scientists to push deeper. They appear in the equations like echoes of possibilities that might lie waiting for us in places we have yet to see. And in the realm of quantum mechanics, where particles seem to dance to rules that defy our everyday understanding, some wonder if tiny fleeting loops might already exist at the smallest scales, hidden among the uncertainties and probabilities that shape our world. So tonight, as you settle into your pillow and let your thoughts drift, imagine a trail that circles back on itself in the quiet forest of time. Picture yourself stepping gently onto that path, feeling each moment fold around you until yesterday and today touch fingertips. It is a reminder that even in a universe that seems to love straight lines and forward arrows, there may still be hidden curves waiting for the day when our minds and our tools are ready to find them. Until then, the loops remain softly coiled in the fabric of possibility, secret pathways through time, waiting for curious dreamers to wander by. Among all the puzzles and thought experiments that swirl around the idea of traveling backward through time, one stands out like a single thorn on a rose, sharp, impossible to ignore, and ready to prick at the softest part of our logic. It is called the grandfather paradox, and it has been troubling physicists and philosophers ever since people first began to take the notion of time travel seriously. If you have ever imagined stepping through a portal to the past, you have probably stumbled across this mind-bending riddle yourself. The paradox is simple to describe but dizzying once you follow its threads. Imagine for a moment that you have built yourself a time machine. It hums gently in your backyard shed, waiting for you to slip inside and push the buttons that will carry you backward through the years. You decide, perhaps out of curiosity or some darker impulse, to travel back to a time before your parents were ever born. You stand there, watching your young grandfather walking down a quiet street, unaware of what the future holds, and now the question hangs heavy in the air. What would happen if you did something to prevent him from meeting your grandmother? Or worse, what if you did something that prevented him from surviving at all? If you succeeded, your grandfather would never have children, your parent would never be born, and without your parent, you would never exist to build that time machine in the first place. But if you never existed, how could you have traveled back and changed the past? And if you did not travel back, then your grandfather would live, your parent would be born, and so would you, giving you the chance to go back and change things all over again. It is a loop that spins endlessly, a snake eating its own tail, twisting cause and effect until they tangle into a knot the universe seems unwilling to untie. This paradox is not just a story for science fiction. It is a deep question about how our reality holds itself together. Our everyday world depends on the chain of cause and effect. Every moment leans on the moment before it, like a line of dominoes falling one after another. The grandfather paradox asks what happens when you flick your finger into that line and knock down the dominoes that led to your own existence. Does the chain snap? Does reality rewrite itself? Or does something even stranger happen? Some physicists and philosophers have tried to find ways around this troubling loop. One idea is that the universe simply forbids paradoxes like this from happening at all. If you stepped back in time, you might find that every attempt to change something important would fail in the end. Maybe you would drop the rock that was meant to startle your grandfather into crossing the street at the wrong time, but he would stumble at the last second and step back onto his original path. The universe, in this view, would protect its timeline with an invisible force, nudging events back into place no matter how hard you tried to push them aside. Another idea is that the grandfather paradox does not prevent backward time travel. It just creates a new branch of reality each time you interfere. This is where the many worlds interpretation of quantum mechanics often comes into the conversation. According to this theory, every choice, every possible outcome spins off its own new universe. If you traveled back and changed your grandfather's fate, you would not erase yourself. Instead, you would step into a parallel timeline where you were never born, while your original timeline, the one where you grew up and built your time machine, remains untouched. In this way, the paradox dissolves into an endless tree of branching worlds, each one holding its own version of history. But this solution raises its own questions. If every backward journey spawns a new universe, how could you ever get back to the one you left behind? Would you become an eternal traveler, lost among infinite timelines, never able to return to the people and places you once called home? And if these countless universes do exist, where are they? Are they hidden alongside our own, waiting in dimensions we have yet to uncover? For now, the grandfather paradox remains one of the strongest arguments against practical backward time travel. It whispers to us that the past may be more firmly rooted than we like to think, its moments locked in place to protect the fabric of cause and effect. It is a reminder that time is not just a line we walk along, but a fragile web of connections, each strand holding another in place. So tonight, as you drift off to sleep, imagine that old street where your young grandfather once walked. Picture yourself standing in the shadows, watching the chain of events that one day led to you. There is a wonder in knowing that every moment, every choice, every heartbeat is part of a story that cannot be easily unwound. And maybe that is the real gift of the grandfather paradox, a quiet nudge to treasure the past for what it is, a path that shaped you exactly as you are, unchangeable and beautiful in its own tangled, perfect way. If you have ever wondered what really happens when you stand at a crossroads in life, you have touched the edge of an idea that has fascinated scientists and dreamers for decades. What if every choice you make, every step left instead of right, every word spoken or left unsaid, spins off a new thread of reality? What if instead of one single timeline marching forward, the universe is actually a grand shimmering tree, endlessly branching into countless versions of what could be? This is the heart of the many worlds theory. It is one of the most surprising and mind-stretching twists to come out of the strange realm of quantum mechanics, the science that explores how the tiniest particles in our universe behave. Quantum mechanics is full of puzzles. At the scale of electrons and photons, things do not behave in the neat, predictable way we see in our everyday world. Particles can exist in multiple states at once. They can act like waves and particles at the same time. They can be connected across vast distances in ways that seem to defy common sense. Back in the 1950s, a young physicist named Hugh Everett looked at all this quantum strangeness and asked a simple but daring question. What if every possible outcome of every quantum event actually happens, just not all in the same universe? His answer became the many worlds interpretation. In this view, when a particle chooses its path, the universe does not collapse the possibilities into just one outcome. Instead, it gently branches, allowing every possible version to play out in its own slice of reality. Picture this for a moment. Imagine a single decision you made today. Maybe you stopped at a cafe on your way home instead of going straight back. In that tiny choice, a branch may have formed. One version of you sits sipping coffee, another version never stepped through that cafe door. Now expand that idea to every moment of your life, every heartbeat, every word, each possibility spinning out new worlds like leaves unfurling on an infinite tree. In the many worlds view, the universe is not a single path, but a vast forest of paths that exist side by side, each as real as the next. But what does this have to do with time travel? In the world of paradoxes, the many worlds theory offers a comforting loophole. Remember the grandfather paradox, that twisty knot where you might go back in time and prevent your own birth, only to find you could never have gone back at all. In many worlds, that knot untangles itself. When you travel backward and change something important, you do not erase the timeline you came from. Instead, you branch off into a new one. In one universe, your grandfather lives, your parents are born, and so are you. In another, your actions spin off a world where events unfold differently, but your original path remains untouched, safely coiled in its own branch. This means, at least in theory, that backward time travel would not create paradoxes that break the universe. Instead, it would make the universe even bigger, spinning off a new timeline each time you change the past. You might never find your way home again, but you would not unravel the thread that brought you there in the first place. Of course, the many worlds theory is still just that, a theory. We do not yet have a way to peek into these parallel branches and confirm they are really out there. Some physicists argue that they exist only in the math, not in reality. Others believe that quantum experiments already hint at hidden worlds, quietly shaping the particles we see and touch. And every so often, in our ordinary lives, we catch ourselves wondering if there is a version of us somewhere who made a different choice, who stayed, who left, who said yes instead of no. Perhaps this is why the idea sticks with us. It is comforting to think that every possibility is real somewhere, that no dream or regret is ever truly lost. It means that when we stand at a fork in the road, we are not locked into just one fate, but part of a universe so rich that it can hold every version of our story. And if time travel were ever possible, the many worlds theory might be the safety net that lets us wander backward without tearing holes in the fabric of reality. So tonight, as you drift off to sleep, imagine all those other versions of you walking along their own branches of the great cosmic tree. Picture them living out the choices you did not make, loving, learning, laughing in ways you can only guess. Somewhere out there, in a universe that never stops branching, the story of you is forever unfolding, each twist and turn a reminder that the universe is bigger, stranger, and more beautiful than we can yet fully understand. And maybe, just maybe, it is big enough to hold all the time travelers our dreams can carry. If you have followed the twists and turns of time travel so far, you know that moving forward in time is easy. We do it every second, every heartbeat, every gentle tick of the clock by your bed. and speeding up that forward journey is possible too, at least in tiny ways, thanks to time dilation and the warping power of gravity. But every time we turn our gaze backward, hoping to slip through the doorway of yesterday, we find ourselves face to face with a stubborn universe that seems determined to keep the past safely locked away. One of the reasons for this cosmic resistance has to do with the simple but profound principle of causality, the idea that causes come before effects. You strike a match and the flame appears. You speak a word and only then does the echo bounce back to you. This smooth, one-way flow of events holds our reality together like stitches in a warm quilt. Without it, life would feel like a jumble of broken pieces, moments colliding out of order, stories unraveling before they have even begun. Over the centuries, our best equations have whispered hints that backward time travel might be possible under the strangest circumstances. We have explored wormholes, cosmic strings, spinning cylinders, and closed time-like curves, all the exotic shapes that space-time might twist itself into, given the right conditions. But each of these ideas brings with it the same troubling guest, the paradox. The idea that you might do something in the past that would erase the cause of your own actions in the first place. It was this tangle of logic that captured the attention of one of the greatest minds of our time, Stephen Hawking. Hawking, who spent his life peering into the darkest corners of black holes in the earliest moments of the universe, knew that paradoxes like the grandfather paradox were more than just playful puzzles. They threatened to break the delicate chain of causality that lets the universe unfold in an orderly way. To explain how the universe might defend itself, Hawking proposed what he called the chronology protection conjecture. In simple terms, it is the idea that the laws of physics may include hidden safety nets that prevent backward time travel from ever becoming possible on a large scale. In his words, it seems that there is a chronology protection agency which prevents the appearance of closed time-like curves and so makes the universe safe for historians. But how might this cosmic protection work? One clue lies in the strange behavior of quantum particles and the energy that surrounds them. If you were to build a time machine, perhaps using a wormhole to connect 2 points in time, you would create a kind of loop where energy could circulate endlessly. This circulating energy could become so intense that it would distort the fabric of space-time, collapsing the very passage you were hoping to travel through. In this way, the universe would slam the door shut just as you tried to step through it, saving itself from paradoxes before they could ever take root. Other physicists have explored similar ideas, wondering if the tiniest fluctuations in quantum fields would always bubble up around a potential time loop, growing large enough to destroy it before it could fully form. Even the smallest imperfections in the structure of space-time might be enough to unravel the conditions needed for backward travel. It is as if the universe has built-in tripwires that snap shut whenever we push too close to tearing apart its carefully woven timeline. This does not mean that backward time travel is entirely ruled out forever. Some solutions still live in the edges of our equations: exotic matter, negative energy, and hidden dimensions. But so far, each time we try to build a bridge to yesterday, nature seems to whisper no. And maybe that is not such a bad thing. After all, the past holds our mistakes and our memories, the things that shape who we are. If it were too easy to wander back and change them, the present might lose its meaning, and the future might become impossible to trust. In a strange way, the universe's fierce protection of its own timeline is a gift. It keeps the story of everything moving forward, free from tangled contradictions that could unravel the lives we know. It gives us the freedom to learn and grow, to accept that each moment is precious, because it cannot be undone. It reminds us that the past, once lived, becomes something sacred, a collection of footsteps behind us that we can remember but not retrace. So tonight, as you drift off to sleep, picture Hawking's Chronology Protection Agency, a quiet guardian that sits at the edge of wormholes and spinning cylinders, gently closing the door before paradoxes slip through. Imagine it like a cosmic librarian, carefully filing away each page of the universe's history where it belongs, keeping yesterday safe from our meddling hands. Maybe one day, if we discover something the laws of physics have not yet revealed, we will find a loophole that lets us peek behind that door. Until then, we live in a universe that moves forward, one tick at a time, a place where the past is a story written in the stars, too precious to rewrite, and just mysterious enough to keep our dreams wandering. If you close your eyes and listen to the soft hum of the universe, you might think time flows only one way, that each moment slips quietly into the next, carrying us forward like leaves drifting down a slow-moving river. But in the secret world of the very small, the strange and jittery realm of quantum mechanics, the river does not always follow the neat path we expect. Sometimes it curls back on itself. Sometimes it hints that cause and effect might not be as simple as we once believed. Over the last century, physicists have devised delicate experiments to test the edges of reality, each one like a lantern held up to the darkness, revealing glimpses of tiny time loops and backward ripples that defy our everyday sense of order. These experiments do not open giant portals to yesterday, but they whisper that the universe, in its smallest parts, may be far more flexible than we can see with our sleepy human eyes. One of the most famous puzzles that makes scientists scratch their heads is the delayed choice experiment. It begins with something called the double slit experiment, a simple but astonishing demonstration of how particles like photons or electrons can behave like waves. When you fire a stream of particles at a barrier with two tiny openings and place a detector behind it, you expect to see two neat piles, but instead, you see an interference pattern, like ripples overlapping in a pond. This pattern shows that each particle somehow passes through both slits at once, behaving like a wave. Now comes the twist. If you place a detector at the slits to check which path each particle takes, the interference pattern disappears. The particle seems to decide to act like a particle instead of a wave. It is as if the simple act of watching collapses the possibilities into one reality. The delayed choice experiment pushes this even further. Imagine that you decide whether or not to observe which slit the particle goes through only after the particle has already passed the barrier. Strangely, the outcome still changes to match your choice. It is as if your decision in the present reaches back in time to alter what the particle did in the past. Does this mean we have found tiny time loops? Not exactly, but it does suggest that the universe at the quantum level does not care about our tidy line between before and after. Cause and effect blur together. What we choose to measure now can ripple backward, deciding how the story unfolded moments ago. Another clue comes from the baffling world of quantum entanglement. When two particles become entangled, they are connected in a way that transcends distance. Change something about one particle, and its partner responds instantly, even if they are separated by light years. Albert Einstein famously called this spooky action at a distance because it seemed to violate the cosmic speed limit. Nothing is supposed to travel faster than light. But experiments have confirmed that entanglement is real, and it raises questions about how information flows in the quantum realm. Some researchers have wondered if entanglement could be a sign of tiny closed loops in time, moments when the flow of information circles back, weaving connections that defy our ordinary sense of before and after. A few bold physicists have even proposed theoretical models where entangled particles communicate through these subtle time loops, sidestepping the need for signals to travel at impossible speeds. Then there are quantum eraser experiments, a cousin of the delayed choice experiment, which make the puzzle even stranger. In these setups, a pair of entangled particles is created. One particle goes to a detector that can measure its path, while the other flies away to another detector. The curious part is that changing how you measure the second particle can erase or restore the interference pattern in the first, even after it has been recorded. It is as if the universe allows the outcome to be rewritten in a tiny loop, blurring the past and future into a single shimmering possibility. Of course, these experiments do not mean you can build a time machine out of entangled particles or delayed choices. These hints of time loops exist only in the delicate dance of quantum probabilities. They are so tiny and fragile that they cannot be scaled up to carry people or spaceships or letters to the past. But they do remind us that the deep laws of nature are not always as rigid as the ticking of our clocks would suggest. When you think about these tiny time loops, it helps to picture the universe like a vast tapestry woven from threads that twist and cross in countless ways. In our everyday world, the threads run mostly straight, pulling us from yesterday to today to tomorrow. But in the quantum realm, the threads sometimes bend and curl back, stitching moments together in ways that feel impossible to us. They hint that time, like space, might be a playground for possibilities we are only beginning to understand. So tonight, as you drift closer to sleep, imagine those particles dancing in the darkness, weaving tiny loops through the fabric of reality. Think of the scientists who stay up late at night, peering into the quantum world for signs of how our universe holds its secrets. And remember that while we may not yet slip backward through time the way we dream, in the smallest corners of existence, the story of time is still full of gentle twists, waiting for curious minds to find them. If you ever find yourself wandering through the gentle countryside of Switzerland and France, you might not even realize that buried deep beneath the green fields and sleepy villages lies one of the most remarkable machines humans have ever built. It is called the Large Hadron Collider, the LHC for short, and it is like a giant circular racetrack for particles. But instead of cars roaring around curves, the LHC sends subatomic particles whirling near the speed of light, pushing the very limits of nature, and in doing so, revealing the strange ways that time itself can stretch and twist at the smallest scales. The LHC is the world's largest and most powerful particle accelerator. It is a ring more than 17 miles long, where protons and other particles are hurled around by massive magnets, reaching speeds so close to light that they would circle the Earth 7 times in a single second. When these particles collide, they smash apart in tiny fireworks that give scientists precious glimpses into the building blocks of our universe, hints about how everything we see and touch is stitched together. But what makes this machine so magical for anyone curious about time is not just what the collisions reveal about matter and energy, but what they whisper about how time behaves when you move incredibly fast. When you push a particle to near light speed, something remarkable happens. The faster it goes, the slower its own tiny clock ticks compared to a clock sitting still on Earth. This is time dilation in its rawest, purest form, playing out billions of times a second inside the tunnels of the LHC. One of the best examples comes from observing particles called muons. Muons are a type of fundamental particle, similar to electrons but much heavier. They appear naturally in the upper atmosphere when cosmic rays from space strike the Earth. Here's the puzzle. Muons have a very short lifespan. When created in the lab or in the atmosphere, they exist for only about 2 millionths of a second before decaying into other particles. If you do the math, they should not be able to travel far before disappearing. Yet every day, billions of muons created by cosmic rays reach the ground and even pass through your body. How is this possible? The answer is that these particles are moving so quickly that time slows down for them. To a muon rocketing through the atmosphere at near light speed, its brief lifespan stretches long enough to cross many miles before it decays. To us, watching from the Earth's surface, it looks like the muon defies its own lifetime. But really, the muon is experiencing time more slowly than we are. It is a tiny time traveler, proving that speed can bend the river of moments that flows through its existence. Inside the LHC, scientists use this same effect to study unstable particles that would normally decay in an instant. By accelerating them to incredible speeds, they stretch their lifespans long enough to capture their secrets. These fleeting particles live just a heartbeat longer than they should, not by magic, but by the beautiful bendiness of time itself. All of this happens at a scale so small we could never notice it in our daily lives. We cannot build a ship that sails near light speed, not yet. We cannot feel our own clocks slow down when we run for the bus or fly in an airplane. But here, beneath those fields, in the humming tunnels of the LHC, we see the universe reminding us that time is not fixed. It breathes and flexes, changing its pace for anyone bold enough or small enough to ride close to light's cosmic speed limit. Some researchers even wonder if the behavior of particles at these speeds might hold the first tiny clues to bigger ideas about time. Could these quantum tricks hint at how nature hides its paradoxes? Could they one day help us understand how to bend time's arrow in larger, more dramatic ways? For now, those dreams are still far ahead of us, waiting for the next generation of curious minds. So tonight, as you settle deeper under your blankets, imagine those particles racing through the darkness below the fields of Europe. Imagine them spinning so fast that their tiny ticking clocks barely move, while our own seconds drift gently on. It is a quiet reminder that even in the hidden places of our world, in giant machines buried underground, in the tiny flashes of particles that flicker and fade, the universe keeps showing us how time is never as simple as it seems. And maybe, just maybe, these small whispers from the quantum world will one day grow into the keys we need to unlock the deeper secrets of time itself, secrets waiting to be found by anyone willing to chase them at the very edge of light's long, mysterious path. If you have been drifting with me through these sleepy chapters so far, you already know one comforting truth about time travel. It is not all wild science fiction or far-off fantasy. We may not have gleaming silver machines with blinking lights and swirling portals. We may not yet have the keys to slip backward through the years and stand beside ancient kings or dinosaurs. But every single one of us is, in a way, a time traveler. Moving forward through time is the one adventure every living thing shares. Every heartbeat, every drifting cloud, every spinning planet. Yet what makes our journey through time so remarkable is that we have discovered ways to bend it, to stretch it, to make the river of moments flow differently for different travelers. Time travel to the future is not just possible, it is already happening, proven by the same physics that keep our satellites orbiting, our GPS working, and our astronauts circling high above Earth. At the heart of this quiet magic is one idea. Time is not a constant tick-tock that beats the same for everyone, everywhere. It breathes and bends, shaped by two powerful forces, speed and gravity. The faster you move through space, the slower you drift through time compared to someone standing still. The deeper you sit in a strong gravitational field, the more gently your clock ticks, stretching your seconds ever so slightly. Take, for example, the astronauts who live and work aboard the International Space Station. Up there, they circle the Earth at nearly 17,000 miles per hour, riding a metal home that glides through the edge of space. Because they are moving so fast, time passes just a tiny bit slower for them than it does for you and me down here on the ground. When they return, they have aged a fraction of a second less than they would have if they had stayed home. They have skipped by the tiniest measure into the future, proof that speed can stretch the flow of time. This is not just a dreamy thought experiment. It is a truth we measure and correct for every day. GPS satellites that help you find your way home rely on clocks so precise that even tiny differences matter. Those satellites orbit high above Earth, where gravity is weaker and their speeds are high. Both effects, speed and reduced gravity, make the satellite clocks tick at a slightly different pace than clocks on Earth. Without adjusting for these differences, your GPS directions would drift miles off course within hours. It is a gentle but constant reminder that time travel to the future is built into the very technology that guides our everyday lives. And while these tiny leaps forward in time are subtle, the physics behind them does not care about scale. In theory, if you could build a ship that flew close to the speed of light, you could step into the future in dramatic, breathtaking ways. Imagine climbing aboard a starship that accelerates to 99% of light's speed. To you, the traveler inside, months or years might pass in the hum of engines and the glow of distant stars. But when you return to Earth, decades or centuries might have drifted by for everyone else. The people you once knew would be gone, their grandchildren's grandchildren standing in their place. You would have skipped ahead, carried on the back of time's bending nature. Even gravity itself offers us a window into this possible future travel. Near a black hole, the pull of gravity is so fierce that time slows to a crawl for anything hovering near its edge. Imagine finding a massive black hole, far from any danger of being torn apart. If you could park a ship just outside its event horizon, the point where light and time slip away, you could watch the universe race ahead while you linger in your slow pocket of seconds. A single hour close to that black hole could mean centuries unfolding beyond your window. For now, these wild journeys remain ideas on paper and scenes in our imagination. Our bodies and our machines are not yet strong enough to ride the edge of a black hole's gravity or to accelerate to light speed without tearing apart. But every equation, every satellite orbit, every particle that lives longer in a collider because of its speed, they all remind us that forward time travel is not just real, it is a guarantee, an open door carved into the fabric of the universe. So tonight, as you close your eyes and drift into sleep, remember that you too are a traveler. With every breath, every heartbeat, you are moving forward, carried by the gentle current of time. And somewhere out there, in the deep darkness between stars, the universe holds the promise that one day, with courage and curiosity, we may build ships that ride these currents faster and further than we ever dreamed. Until then, we keep studying, keep wondering, and keep drifting, step by tiny step, into the waiting arms of tomorrow. It is easy to think of time travel as something that lives only in science fiction stories or distant galaxies. But the truth is, a quiet miracle of time bending is working for you every single day, hidden right there in your pocket or resting in your hand as you read these words. I am talking about the Global Positioning System, GPS, that tiny marvel inside your phone that knows exactly where you are on this spinning planet. It is easy to take for granted, this blue dot on a glowing screen guiding you through unfamiliar streets or helping you find the fastest way home. But behind that dot is a dance of clocks and satellites that would fail completely if not for the strange elastic rules of time itself. Let's drift up for a moment, far above your rooftop, past drifting clouds and the hush of the upper atmosphere, all the way to an altitude of about 12,000 miles. There, speeding through the darkness, orbit more than 30 satellites that make up the GPS network. Each satellite loops the Earth twice a day at a speed of roughly 8,700 miles per hour, its path precisely calculated to cover every inch of the globe below. On board each of these satellites is an atomic clock, one of the most accurate timepieces ever built by human hands. These clocks keep time so precisely that they would lose or gain only a billionth of a second in a day. You might wonder why such extreme accuracy matters. After all, how could a tiny shift in time possibly change the map on your phone? The answer is simple, but astonishing. Your phone's GPS does not work by measuring distance alone. It works by measuring time. Each satellite constantly beams out a signal that tells the exact moment it left that satellite's clock. Your phone listens to signals from multiple satellites at once. By comparing the time it takes each signal to arrive, it calculates how far away each satellite must be. With this information, your phone can pinpoint your location on Earth within a few feet. It is like listening to a chorus of whispers from space and using those whispers to draw a perfect dot on a map. But here is where nature's playful bending of time steps in. Remember Einstein's revelations. Time is not an unwavering metronome. It changes depending on how fast you move and how strong gravity pulls at you. GPS satellites orbit high above Earth's surface, where the pull of gravity is weaker than it is down here where you stand. According to general relativity, this weaker gravity makes the satellite's clocks run faster than identical clocks on the ground. But at the same time, special relativity says that because the satellites are moving so quickly through space, their clocks should actually tick slower than ours. The result is a cosmic tug-of-war. The weaker gravity pulls time forward by about 45 microseconds every day. The fast speed pulls time backward by about 7 microseconds. When you add these effects together, each GPS satellite's clock runs ahead of clocks on Earth by about 38 microseconds every single day. That might sound like nothing, less than a millionth of a second, but in the language of GPS, that tiny drift is enormous. If the system did not adjust for this daily slip, your position on Earth could be wrong by miles within minutes. The blue dot that guides you to your favorite cafe would drift across rivers, wander into forests, or leave you lost in a parking lot far from where you meant to be. To keep this from happening, engineers built Einstein's corrections right into the heart of GPS. The satellite's clocks are tweaked before launch, so that once they settle into orbit, their faster ticking matches Earth time. Ground stations constantly monitor the satellites and send updates to make sure they stay in sync. It is an invisible ballet, a real-life proof that time is not a stubborn constant, but a shape-shifting partner in the dance of navigation. Sometimes when you hold your phone and see that little blue dot, it is easy to forget how much wonder lives inside that tiny piece of glass and metal. It is easy to forget that each map you check depends on clocks floating high above, ticking in a way that proves relativity is not just an abstract theory, but a living rule of our everyday world. So tonight, as you lie in bed and drift towards sleep, imagine those satellites circling quietly overhead. Picture each one carrying its precise clock, singing its time signal down through the darkness, past the hush of the atmosphere, to your phone glowing softly beside you. You are not just using technology when you tap that map, you are witnessing a hidden conversation between the bending of time and the pull of Earth's gravity. A conversation that keeps you connected, keeps you found, and gently reminds you that even our smallest journeys rest on the greatest truths the universe has to share. Maybe in that small blue dot we find a promise too, that time can flex and sway, that our dreams of traveling through it are not only for starships and silver machines, but for the everyday magic already humming quietly in our pockets. As we drift further into this gentle exploration of time's mysteries, we come to the question that sparkles at the heart of countless books, late-night conversations, and childhood daydreams. Could we ever build a real-time machine, a vessel not just for thoughts and theories, but one you could step inside, press a button, and find yourself drifting through the currents of yesterday or tomorrow? To answer that, we have to hold two truths side by side. First, the laws of physics, those beautiful, precise equations that have carried us to the moon and back, do not slam the door entirely shut on the idea. They bend in surprising ways, leaving cracks in reality that whisper, maybe. But the second truth is just as important. The bridge between what is possible in theory and what we can build in reality is wider than any canyon on Earth. And for now, that bridge is made of dreams more than steel. Let's begin with what the physics says. We know from Einstein's theory of relativity that moving forward in time faster than our normal pace is possible. It happens every day to astronauts circling Earth, to particles racing through accelerators, and to clocks perched high on satellites. We know that massive gravitational fields, like those near black holes, slow time down for anything caught in their embrace. So a machine that could ride these forces, traveling at near light speed, or hovering near a cosmic giant, could, in theory, carry you far into the future. But building a craft that can reach those speeds or survive those gravitational extremes is a mountain of a challenge all by itself. Backward travel is where things get especially tangled. The equations of general relativity allow strange shapes in space-time, closed time-like curves, wormholes, Tipler cylinders, cosmic strings that suggest pathways looping back to yesterday. But each of these ideas demands conditions that seem impossible to reach with any technology we can imagine today. For example, a stable wormhole might allow a shortcut between two distant points in space-time. Some clever minds have proposed that if you could accelerate one end close to light speed and bring it back, the two ends might be offset in time. Step through one, and you step into the past or the future. But that "if" is enormous. First, you would need exotic matter with negative energy density to hold the wormhole open against the crushing force of its own gravity. This is not the kind of matter that makes up stars or apples or you and me. It is a hypothetical stuff that might exist in tiny amounts at the quantum level, but no one has ever found a way to harvest it, let alone generate enough to keep a human-sized tunnel stable. Even if we found it, we would need to figure out how to manipulate it safely, shaping it into the scaffolding that would stop a wormhole from collapsing the instant you stepped inside. Then there is the staggering amount of energy required to bend space-time enough for backward travel. The energy needed would likely dwarf anything humanity has ever produced. It would make our biggest power plants look like candles flickering in the wind. Some estimates suggest you would need the mass energy equivalent of an entire star just to open a single wormhole large enough to walk through. And then you would have to control that energy, keep it stable, and protect yourself from the intense radiation that would almost certainly burst from the tunnel's walls. Even beyond the exotic matter and the energy, there are the paradoxes and instabilities. Quantum effects might bubble up around any time loop, destroying it before it can form. Hawking's chronology protection conjecture suggests the universe has built-in safeguards against backward time travel, like a cosmic bouncer standing at the door to yesterday, turning away any would-be time tourists. But does that mean the dream is pointless? Not at all. The very act of thinking about time machines stretches our understanding. It pushes physicists and engineers to test the boundaries of what we know, from the structure of wormholes to the hunt for quantum loopholes that might someday be real. It inspires new ideas about energy, propulsion, and the fabric of the cosmos itself. And maybe, just maybe, the future will surprise us. A few hundred years ago, the idea of flying through the sky in a metal ship would have sounded just as impossible. So would sending messages through the air or carrying the sum of human knowledge in a tiny device in your pocket. Each leap came when curiosity met courage and when our tools finally caught up to our dreams. So tonight, as you close your eyes, let the thought of a real time machine drift through your mind like a soft echo from tomorrow. Picture engineers sketching designs in hidden labs. Imagine scientists bending over chalkboards covered in tangled equations, daring the laws of nature to reveal one more secret. Maybe we will never ride a machine that takes us back to yesterday, but the hope, the wondering, the questions, those are time machines all on their own. They carry us forward, one idea at a time, into futures we can barely imagine, and they remind us that the greatest journeys always begin with the quietest question: what if? For as long as we have dreamed about stepping outside the flow of time, we have also whispered to ourselves an uneasy truth. The universe does not give up its deepest secrets without a cost. Time travel, especially the backward kind, is one of those dreams that comes wrapped in shadows, a wonder that might carry hidden dangers for anyone bold or reckless enough to try bending the river of moments back on itself. When we think about building a time machine, it is easy to picture gleaming control panels and humming energy fields, maybe even a safe glowing tunnel that leads you gently from today to yesterday. But the real universe is not so polite. It is made of searing radiation, swirling gravitational forces, and unpredictable quantum tricks that can shred even the simplest plan. Each idea for how we might journey back carries its own nest of risks, and the closer you look, the more you realize that playing with time might come at a price no traveler could ever pay. Consider wormholes, those hypothetical cosmic tunnels that could, in theory, connect two distant points in space and time. The equations tell us that if you could keep one mouth of a wormhole moving close to the speed of light and bring it back, you might offset the two ends in time. One side could open in the future, the other in the past. Step through, and you step backward. But before you imagine parking a wormhole in your backyard, think of the physics that keeps it stable. To prevent the tunnel from collapsing under its own immense gravity, you would need exotic matter with negative energy. Not only is this exotic matter purely theoretical, but its behavior would be wildly unstable if you tried to shape it into something large enough for a human to crawl through. Even if you somehow found or created enough of this strange material, the tunnel's walls would not be a calm, silent hallway. They would be bathed in intense radiation. As particles zip back and forth through the loop of space-time, they could create a feedback effect, a growing storm of energy that builds to catastrophic levels. Many physicists believe this feedback would destroy the wormhole before you ever had the chance to step through, or worse, tear apart anything that tried to pass within. The very fabric of space-time would fight back, slamming the door shut with a blast of cosmic force. And then there are black holes, nature's ultimate time-bending machines. Hover near the edge of a massive black hole, and time slows dramatically compared to the rest of the universe. But getting that close means dealing with tidal forces so strong they can stretch and crush anything that dares to approach. The radiation near a black hole is intense too. Powerful jets of high-energy particles and X-rays can shred a spaceship's shielding, not to mention what they might do to a fragile human body inside. You might survive the warping of time only to be undone by the searing energy needed to make it possible. Some researchers have even wondered if building a time machine could create paradoxes so severe that the universe itself would react violently to prevent them. Stephen Hawking's chronology protection conjecture is one idea for how this might happen. It suggests that tiny fluctuations in quantum fields would bubble up near any closed time-like curve, a loop in space-time that allows backward travel, and amplify into a destructive burst of energy, snapping the loop before a paradox can be born. It is as if the universe has built-in alarms, tripping whenever we push our luck too far. Beyond physics, there is the chilling thought of what time travel might do to the traveler's mind. Imagine stepping out into the past only to find that you do not quite fit anymore, that you have brought back pieces of the future that warp events in ways you cannot predict. The paradoxes could twist the story of your life into knots. You might erase your own reasons for stepping back in the first place, or worse, break the chain of cause and effect that holds your memories together. Would you still be you if the events that shaped you were undone? These dangers do not mean we should stop wondering. After all, every scientific breakthrough comes with risks that once seemed insurmountable. Electricity, nuclear power, flight into space. But the difference with time travel is that the stakes are not just physical or technological. They cut to the heart of what it means to live in a universe bound by rules that keep the past and future separate. Messing with that boundary could ripple outward, changing everything or destroying everything in ways we might never see coming until it is too late. So tonight, as you drift off to sleep, imagine those flickering wormholes and swirling black holes at the edges of the cosmos. Picture the brave souls who dream of stepping through, armed with equations and courage, and the hope that nature's barriers can be softened. And remember that sometimes the greatest mysteries are beautiful, not because they are easy to reach, but because they remind us how precious our fragile place in the flow of time really is. Perhaps in the end, the real gift is not finding a way to break yesterday open, but learning to cherish each moment for the fleeting, unstoppable miracle that it already is. When you sit quietly beneath a sky scattered with stars, it is easy to feel small, yet if you listen closely, you may sense something else too, that tiny spark that has always lived in us, urging us to ask questions bigger than ourselves. Few questions stretch our imagination as boldly as the idea of time travel. It is a dream that reaches back to our earliest myths and pushes forward into the edge of tomorrow's science. But maybe its greatest gift is not whether it will ever be real in the way we hope, but how it stirs us to keep exploring the strangest corners of reality. Think about what happens the moment you start to wonder, could we ever visit yesterday? Could we stand beside tomorrow? That simple spark of curiosity cracks open doors that lead us into the deepest puzzles of our universe. We are forced to reckon with how time actually works, not just as a ticking clock on the wall, but as a dimension woven together with space, gravity, and motion. To ask about time travel is to ask about the nature of reality itself. Long before we could even test these ideas in the lab, ancient people imagined time as a river or a circle, something alive, something not always linear. When scientists finally put equations to that intuition, the dream of time travel nudged them to uncover hidden truths that might have stayed buried. Einstein's theory of relativity, for example, is now the bedrock for how we understand time's elasticity, how it stretches and slows for objects moving fast or caught in the deep well of gravity near a massive star. But would we have asked how to bend time at all if we were not enchanted by the idea of stepping outside its ordinary flow? Every corner of theoretical physics has been brightened by this curiosity. When we wonder about backward time travel, we are drawn to study black holes, cosmic giants that warp time so severely they almost freeze it at their event horizons. When we dream up wormholes as tunnels that could shortcut through time, we have to understand how gravity bends space-time and whether exotic matter could hold those tunnels open. Each new question pulls us deeper into quantum mechanics too, the strange realm where particles slip between possibilities and seem to blur the lines of cause and effect. Even the wildest paradoxes, like the grandfather paradox, push us to think more clearly about cause and effect and about whether the universe has built-in safeguards that protect its own timeline. From these puzzles, we get theories like Hawking's chronology protection conjecture, ideas that spark entire fields of research. It is as if time travel, impossible or not, acts like a lodestar that helps physicists navigate the most mind-bending landscapes of the cosmos. Beyond the math, time travel touches our human story in ways that are harder to measure, but just as real. It makes us wonder what it means to remember, to hope, to dream of changing what has been lost. It teaches us about regret and second chances, about the temptation to rewrite history and the beauty of letting moments stay where they belong. And it reminds us, again and again, that time is precious precisely because we cannot hold it still. If you look around, you will see how this longing fuels more than just physics. It trickles into our literature, our films, our quiet moments of wishing. Writers craft stories that spin time into knots, adventures through wormholes, starships that slip across centuries, lonely travelers who find themselves stranded in eras that no longer fit them. These stories shape how we imagine the future of science. They light a candle for the next curious mind, the next question that dares to peek over the edge of what we know. One day, perhaps the math and the engineering will align, and a real-time machine will flicker into existence. Or perhaps we will find that nature's safeguards are too strong, that time only opens in one direction for us, the one we are already walking together. Either way, the real magic is that time travel invites us to keep pushing. It invites us to imagine what we could build if only we understood one more layer of reality. So tonight, as you drift towards sleep, think about all the minds who have stood beneath the stars, asking the same impossible question. What if time could open for us? Imagine the scientists scribbling equations by candlelight, the dreamers spinning tales around campfires, the children who look up at the night sky and feel the ache to visit faraway tomorrows or forgotten yesterdays. This wonder is a kind of time travel all its own. It carries us forward, fuels our questions, and keeps our curiosity alive, always pulling us toward the next mystery, waiting just beyond the bend in the river of time. Sometimes, the softest place to rest our heads is right where science and story meet. For all the equations and careful measurements that shape our understanding of the universe, there is something beautifully human about weaving a little imagination into the spaces science has yet to reach. That is where the dreams of time travel truly come alive, in the dance between what is possible and what we dare to dream. Our fascination with traveling through time did not begin with equations scribbled on chalkboards or satellites orbiting above Earth. It began with stories, the ones whispered around flickering fires long before we could measure the speed of light or plot the curve of space-time. Ancient myths spoke of gods who could slip forward and backward through the ages, spirits that could revisit the living, and enchanted objects that could show glimpses of what was yet to come. These early tales were seeds planted in our collective imagination, seeds that would grow into the science fiction stories that keep us so wonderfully curious even now. Look at H.G. Wells, whose novel The Time Machine brought the idea of mechanical time travel to life for the first time. In Wells' world, time was not just a river we drift down helplessly. It was a dimension, like space, that could be crossed if only you built the right device. He wrote about it with the same wonder that physicists would later bring to the theory of relativity. Did Wells have Einstein's equations at his fingertips? Of course not. But his vision created a playground for minds willing to ask, what if? Fast forward to the stories we have now, films, novels, and shows that spin time into 1,000 shapes. We watch heroes leap decades ahead, wander through centuries past, and wrestle with the paradoxes that real scientists still debate today. Back to the Future made us laugh and wonder what might happen if you changed one moment in the past. Doctor Who invited us into a blue police box that can slip anywhere in space and time, a story that has kept generations dreaming about wormholes and time loops long before they read a word about general relativity. But here is the quiet magic. Fiction is not just make-believe, drifting untethered in the wind. It nudges real scientists to dig deeper. Sometimes what starts as a wild dream in a book or a film inspires questions that become the seeds for serious theories. The idea of a wormhole, a tunnel connecting distant parts of the universe, was first called an Einstein-Rosen bridge because two scientists took the flexible fabric of space-time and asked if it might bend back on itself. Yet long before the math was written down, countless stories had imagined secret doors, portals, and hidden corridors through time and space. Science fiction does not always get the details right, and that is okay. It is not meant to be a textbook. It is a promise that our curiosity has no bounds. A time machine in a novel may hum along without worrying about the crushing tidal forces near a black hole or the impossible energy requirements of a stable wormhole. But that same story might lead a curious child to ask, could we really do this? And one day, that same child might become the physicist who takes us one step closer to answering the question for real. Sometimes fiction is even bolder than reality. It shows us what might happen if we could break every natural barrier. What happens if you step back and change your past? Stories take that idea and twist it into paradoxes, heartbreaks, and second chances. They remind us that time travel, for all its physics, is also about longing, our deep wish to fix old regrets, to relive moments we treasure, to peek ahead and see how our story turns out. In this way, fiction speaks to parts of us that pure fact cannot always reach. And yet the science grounds us. It brings balance to our wandering thoughts. It tells us, this is what we know for sure. This is what the math allows. Here are the boundaries nature has drawn so far. The dance between fiction and fact keeps our feet on solid ground, even as our minds drift toward the stars. So tonight, as you close your eyes, hold both in your heart the stories that make you wonder and the science that makes you reach for more. Let them swirl together like galaxies spinning in the dark. Who knows what dreams they might plant? Maybe one day, someone will read a bedtime story about a traveler who slips through time and wake up wanting to know how the universe might really bend to make that happen. In the end, the line between fiction and fact is not a wall but a a place where equations and dreams meet. That bridge is why we keep asking the impossible questions, why we stand beneath the stars and wonder if time might someday open a door just wide enough to step through. And whether we ever find that door or not, we will keep writing stories and building telescopes, keep drifting through this beautiful mystery together, one idea at a time. If there is one reason time travel clings to our imagination so tightly, it may not be because we hope to glimpse tomorrow's world of shining cities or hover cars, nor is it only the thrill of standing in the past watching ancient empires rise and fall with our own eyes. More than anything, time travel stirs something deep inside us because it asks us to face our oldest questions, the ones that have lingered quietly behind every heartbeat since we first began to wonder who we really are. Beneath the science and the equations lies something softer and more human, the question of free will and destiny. If you could slip backward in time, could you change what has already been written? Could you untangle the knots of old mistakes, erase words spoken in anger, hold on a little longer to people you lost too soon? Or is the past a stone path already set, each step a mark you can look at but never lift away? Philosophers have asked these questions for centuries, long before we had words like wormholes or closed time-like curves. Some believe that free will means we are constantly shaping our future, that each decision sends ripples forward, building the world one choice at a time. Others wonder if every choice we make is already woven into a grand tapestry, that fate or destiny holds our hands more firmly than we dare admit. If time loops were real, would they show us we have less freedom than we think, bound forever to repeat the same steps? Or would they reveal that we are more powerful than we can grasp, able to slip out of one path and carve a new one for ourselves? Regret, too, is tied to this dream. Think about it. How many moments in your own life do you carry like small stones in your pocket? Old words you wish you could pull back, chances you wish you had taken, doors you wish you had walked through. We all have a list, whispered to ourselves in the dark, and that is what makes backward time travel so tempting. It promises we could set those stones down. We could go back, slip a warning into our younger hand, change the ending of the story. But would you really want to? For every regret you might undo, there are countless threads tangled with it that you might never expect. Would you still be you if you had made every better choice? The truth is, our mistakes and missteps carve out who we become. They teach us the shape of compassion and the weight of forgiveness. They give our joys their sweetness because we know what it feels like to lose. Change one moment, and you might find you have pulled apart something precious you never meant to touch. And then there is the question of other people's stories. We do not live our lives alone. Each decision we make brushes against the lives of others. If you traveled back and saved a friend from heartbreak, would they still become the strong, resilient person they are today? If you stepped in to fix a small tragedy, could you cause ripples that lead to greater sorrows later? The past is delicate, balanced on so many unseen threads. Our wish to change it often forgets that each moment is part of a bigger shared tale. Some philosophers say that time travel, if it were real, might not be about rewriting, but about understanding. Maybe the gift would not be to fix what went wrong, but to stand in those moments with new eyes, to see our parents as young people making choices in fear and hope, to watch ourselves at crossroads we hardly remember, to feel more compassion for the way we stumbled through growing up. Perhaps time travel's deepest promise is the chance to forgive others and ourselves. So tonight, as you lie there and let your mind drift, think of the story that brought you here. It is not a neat, perfect line. It twists and loops, filled with wrong turns and small miracles, with heartbreaks that made room for new joys you never saw coming. Time travel, real or not, reminds us to cherish our place in that story, to hold our regrets gently, knowing they are stitched into the fabric of who we are. Maybe we do not need a machine to go back. Maybe what we really need is to trust that the path we are walking is enough, that we can forgive the past, live fully in the present, and greet tomorrow, not with the wish to rewrite yesterday, but with the courage to keep writing our story, one honest moment at a time. And perhaps that is the greatest truth hidden in all these theories and dreams, that time travel is less about escaping our mistakes and more about learning to love our beautifully imperfect journey through the river of time. After wandering through so many corners of this puzzle, maybe the greatest comfort is pausing for a moment to ask, what do we truly know for sure about time travel? Not just the stories we love, or the equations that twist themselves into shapes our minds can barely follow, but the simple, steady truths we can hold in our hands like small polished stones. Let's start with the piece that feels almost like magic, but is as real as the ground beneath our feet. Traveling into the future is not just possible, it is guaranteed. Every breath you take, every blink of your eye, is you moving through time. You are a traveler already, even if you do not feel the wind of it against your skin. But nature does more than just carry us forward at the same steady pace. It also gives us a way, however subtle, to stretch that journey. Einstein's theory of relativity told us that time is not a single rhythm ticking out the same for everyone, everywhere. It bends and flexes, slowing down or speeding up, depending on how fast you are moving or how strong gravity's pull is where you stand. Astronauts orbiting Earth on the International Space Station live out this truth every day because they are moving so fast and are farther from Earth's gravity well than we are down here. Their clocks tick ever so slightly slower than ours. When they return home, they have skipped ahead, even if only by a fraction of a second. GPS satellites rely on this same truth. Their onboard clocks are adjusted to keep them in sync with time on Earth, proving that if we ignored the bendiness of time, our modern navigation would drift and fail. So yes, forward travel is not only real, but written into the way the universe works. If you could build a ship that raced close to the speed of light, or if you could hover near the event horizon of a black hole without being torn apart, you could stretch a few hours into decades or centuries. When you returned, the world would have raced ahead without you. It is breathtaking to know that this is not just science fiction. It is a truth that has been measured, calculated, and tested, a promise hidden in the fabric of space-time itself. And yet, what about that deeper dream? The dream of stepping backward, of slipping into the past to stand beside people long gone, or to watch your own footsteps from years before. Here, the universe gives us a softer, more tangled answer. Backward travel is not forbidden in the math. In the deep folds of Einstein's equations and other theories, there are hints that closed time-like curves and strange shapes of space-time, like wormholes or spinning cylinders, could in theory bend time in loops that connect tomorrow with yesterday. But whenever we reach out to touch those loops, nature seems to push back. Those same equations that open tiny cracks for backward travel also demand conditions that border on impossible. You would need exotic matter with negative energy to keep a wormhole stable, but we do not know how to find it, let alone gather it in the amounts needed. You would need energy that makes our largest power plants look like flickering candles. And even if you could build this impossible machine, the universe might defend itself against paradoxes by flooding your time tunnel with a destructive wave of radiation, snapping the loop shut before you ever step through. Stephen Hawking captured this so perfectly when he proposed his chronology protection conjecture, the idea that the universe might have subtle ways of protecting its own timeline. In his words, the universe is safe for historians. The past remains something we can study, cherish, and wonder about, but not something we can rewrite. Perhaps this is nature's gift too, a reminder that the present matters because it cannot be undone, a reminder that the future is something we can shape, but only by stepping forward. So what do we know for sure? We know that the dream of time travel keeps us curious, even when it stays just out of reach. We know that moving forward faster than our normal pace is real, written into the heartbeat of the cosmos. We know that backward travel dances through our equations, but tangles itself in paradoxes and protective barriers that seem to say, not yet and maybe not ever. And still, none of this closes the door. Every satellite we launch, every particle we accelerate near light speed, every black hole we study with telescopes that peer across billions of light years, they remind us that time is not rigid. It bends and ripples in ways we are only beginning to understand. So tonight, as you drift off to sleep, hold this gentle truth close. You are already a traveler. Each sunrise pulls you deeper into the mystery of tomorrow, and whether or not we ever build a machine that carries us backward through yesterday's pages, the real wonder is that we keep asking how time works. We keep exploring its secrets, and in doing so, we remind ourselves that some of the best journeys are the ones we take together, one tiny step, one curious question, one sleepy dream at a time. After wandering through theories that stretch like cosmic ribbons, peeking into black holes, tiptoeing past paradoxes, and listening for whispers of tiny quantum loops, we arrive at the question that tugs at the end of every one of these gentle rambles. Is time travel really possible? It is a question that floats between our hopes and our equations, a question that has no single neat answer, but perhaps the most honest answer is a quiet, cautious yes, with a little asterisk tucked beside it. Let's start with the part that is simple and true, the part that needs no giant machines or exotic matter or spinning cosmic strings. Traveling into the future is not only possible, it is happening right now, woven into the fabric of existence. Every tick of the clock nudges you forward in time. You, me, this planet, every drifting cloud and orbiting moon, we are all moving forward, carried by the gentle current of time's river. But the real wonder is how nature gives us ways to bend that flow. Speed up enough, and time slows down for you. Sit near something massive enough, like a black hole, and the same effect unfolds. Astronauts circling Earth age just a breath slower than those they left behind. Particles in accelerators live longer than they should, their tiny lifespans stretched by the near light speed rush of their journey. This is time travel to the future, written right into the physics we test and trust every day. No magic required, just the beautiful truth that time is not fixed. It flows, flexes, and listens to gravity and speed. So that first yes comes without hesitation. If you want to drift into the future a little faster than those around you, the universe nods its approval. You just need the technology, the courage, and the understanding to push yourself close to light's shimmering edge. But the dream that makes our hearts ache is the other one, the backward step, the longing to peek behind the curtain of yesterday, to wander into the past like a traveler slipping through a hidden door. Here, the universe keeps its secrets closer. The equations in general relativity allow for strange loops in space-time, closed time-like curves, wormholes, spinning Tipler cylinders. They are there in the math, quiet possibilities that say, maybe. Yet every time we lean closer, nature pushes back. To keep a wormhole open, you would need exotic matter with negative energy, something we have never found or created in the amounts required. To spin a cylinder near light speed long enough to loop time, you would need energy that makes a star look like a campfire. And even if you solved these impossible engineering riddles, the universe has its own guards, paradoxes that threaten the story of cause and effect, quantum ripples that might surge up and snap your time machine before it ever hums to life. So is backward time travel possible? The honest answer is yes, in theory, with challenges so colossal they look more like the dreams of science fiction than the blueprints of tomorrow's engineers. That second yes must wear its asterisk proudly, a reminder that just because the door is cracked open in our equations does not mean we are ready to walk through it. But here is where the real wonder blooms. The third yes is the one that matters most. Yes, Cispri, because studying time travel is about more than building machines or slipping through portals. It opens the universe. Every question we ask about bending time forces us to look deeper at how reality works. It pulls us into the heart of black holes, the swirls of quantum entanglement, the ghostly hints of many worlds branching endlessly like a cosmic tree. It pushes scientists to test the limits of energy, matter, and the nature of causality itself. It inspires new generations to scribble equations on chalkboards and sketch impossible engines in the margins of notebooks. It keeps us curious, pulling us toward the edges of what we know, with the promise that there might always be something more waiting in the dark. And perhaps more than any time machine with blinking lights and whirring gears, that curiosity is the real vessel that carries us through time. One question at a time, one idea leading to the next, across generations. It is a kind of time travel all its own, a journey not through wormholes but through wonder. So tonight, as you drift to sleep, hold that asterisk in your heart. Let it remind you that yes, you are already a traveler, moving steadily forward, every second carrying you into tomorrow. Yes, the backward road glimmers in the math, a puzzle that keeps our minds nimble and our eyes wide. And yes, this dream, this impossible longing to step beyond our moment, is exactly what makes us human, a reminder that no matter how far we drift through the cosmos, we will never stop reaching for the secrets that lie just beyond the bend in time's quiet river. And so, dear friend, here we are at the gentle edge of our journey through one of the most beautiful questions ever to drift through a curious mind. We have wandered together through ancient myths and cosmic equations, past spinning cylinders and silent black holes, through tangled paradoxes and quantum whispers so small they slip through our fingers like starlight. We have asked whether time travel is really possible, and what we have found is a simple, quiet truth. Our journey through time is already the greatest adventure we will ever know. If tonight has reminded us of anything, it is that time is not just something to be conquered or bent to our will. It is something to be cherished. Every moment you have lived, every breath you have taken, has carried you forward on a path no one else has ever walked. That path is full of tiny miracles, the soft hush of your mother's voice when you were small, the first time you looked up at the stars and wondered what lies beyond, the warm memories you hold like fireflies in the jar of your mind. These moments cannot be erased or undone, and maybe that is what makes them so precious. Sometimes we wish we could go back to change something, to hold on a little longer, to whisper gentle advice to a younger version of ourselves. And maybe one day, if nature ever loosens its grip on the past, we will stand at that door and choose whether to open it. But until that distant day, we have this, the gift of today. the gift of stepping into tomorrow with open eyes and a heart ready to write the next page. As you drift closer to sleep, I hope you can feel how extraordinary it is that you are here at all, that your atoms were forged in the hearts of ancient stars, their deaths scattering the ingredients that would one day come together to make you, that you are part of a universe that bends and breathes, that you ride the gentle river of time each day, moving steadily toward futures still unwritten, that you stand on the shoulders of everyone who has dreamed before you, the storytellers who imagined golden machines with blinking lights, the physicists who scribbled equations late into the night, the poets who gave time its metaphors and its music. When you close your eyes tonight, I hope you will let yourself imagine what might lie ahead. Maybe one day, long after we are gone, someone will build a ship that rides the curves of space-time like a leaf drifting on a hidden current. Maybe they will slip through a wormhole, protected by exotic matter that today lives only in our equations. Maybe they will stand beneath ancient trees, watching the first sparks of fire that warmed our ancestors, or gaze from the farthest reaches of tomorrow's cities, glittering in starlight. And even if those dreams never come true in the way we hope, what matters most is that we keep wondering, that we keep asking impossible questions, because those questions pull us forward. They remind us that the story is not finished yet, that each moment you live is a chance to shape what comes next, to send ripples into the future that might one day meet someone else who looks up at the same stars and wonders, what if? So, as you settle in and let sleep wash over you, remember this: you are a traveler. Every heartbeat carries you deeper into the undiscovered country of tomorrow. You do not need a machine to be a voyager through time. You only need your dreams, your hopes, and the gentle courage to keep walking forward into the mystery. Thank you for drifting with me tonight, for opening your mind to the big questions, for letting your heart rest in the space where science and wonder meet. If you find comfort in these quiet rambles through life's deepest secrets, please remember you are always welcome here in our cozy corner. And if these stories help you drift into your dreams, let them carry you somewhere beautiful, to hidden pasts, to distant futures, to the soft space in between where we remember how precious our one wild journey through time truly is. Sleep well, fellow traveler. May your dreams be filled with wormholes and starships, gentle what-ifs and warm memories, and may you wake tomorrow with the quiet knowing that each new day is its own small, perfect step through time, a reminder that sometimes the greatest adventure is simply living it, one heartbeat, one breath, one dream at a time. Before you drift fully into sleep, I want to take a moment to thank you truly for wandering through time with me tonight. We have explored ancient myths, tangled paradoxes, distant black holes, and the delicate threads of our own memories. We have reminded ourselves that whether or not we ever build a machine that spins us backward, we are all time travelers already, moving gently forward through the universe, one moment at a time. Your curiosity, your willingness to dream with me, is what makes these gentle explorations so special. It is what keeps this cozy corner alive, a place where science meets wonder, and we remind ourselves that the world, for all its noise and rush, is still full of mysteries waiting to be held softly in our minds. If you find comfort in these sleepy rambles and big questions, I would love for you to stay on this journey with me. Please tap the like button if you enjoyed drifting through time tonight. It lets me know you are out there, listening under your blankets, dreaming just as I am. And if you have not yet subscribed, consider it your little key to keep our lantern of wonder glowing bright. When you subscribe, you help this tiny corner grow into a warm place where more curious souls can gather and dream together. If you ever feel like sharing, I would love to know where you listen from. Where in the world does this quiet voyage find you tonight? Drop a comment and tell me what mysteries you hope we will explore next. Until then, sleep well, keep your heart open to the secrets tucked into every second, and remember, the adventure is not over. There will always be more to wonder about, and I will always be here, ready to drift through it with you. Good night, dear friend, and thank you for dreaming with the Snoozy Scientist.